Hello, my name is Magnus Petersen. This is my tutorial number 22 on TensorFlow, and this is about image captioning. I had not planned on doing this tutorial, but when I did tutorial number 21 on machine translation, I realized that image captioning was basically just machine translation and transfer learning for images. So this tutorial combines tutorial 21 with tutorials number 8 and 10 on transfer learning. And you should see those other tutorials before you see this one, because I won't go into all of the details again. So remember from the previous tutorial on machine translation between human languages that we made a recurrent neural network using what was called an encoder and a decoder. And the encoder would take the input text and process it to generate what we called a thought vector, which was an array of floating point numbers, and it would then input that as the initial state for the recurrent units in the decoder so that they could generate the output text in the destination language. The idea in image captioning is quite similar, but we have replaced the encoder part of the network with a pre-trained image model, and here we will use the VGG16 model that we have also used in previous tutorials. So for example, if we have this input image here, we process that through the convolutional neural network. And normally we would take the output from the last layer, and this would be a vector with 1000 elements. And we would take the index of the highest element, and that would be the output. So for example, here it might output the number 340, and that would be the class for a bear, for example. So what we do in transfer learning is that we ignore the last output layer, which has been trained for the ImageNet dataset, and instead we output the vector from one of the previous layers. So if we take the next to last layer here, which is a dense layer or a fully connected layer, then it outputs a vector with 4096 elements, and we want to use that as the initial state in our decoder so that the decoder knows what are the contents of the image, and then it can transform that into a text. However, in this tutorial we will use an internal state size for the recurrent units of 512 elements. So we have to map a vector with 4096 elements down to only having 512 elements. And we do that by adding an intermediate dense or fully connected layer. And it's important that it has the tanh activation function so that it limits the output between -1 and 1. Otherwise I couldn't get it to work. So what we have now is a vector with 512 elements that summarizes what the image contains. Now the decoder is actually run in two different ways, and I'm not sure I made that entirely clear in the previous tutorial on machine translation. So let me try and make it clear now. We run it differently depending on whether we are doing training or inference. During training, we give the decoder 3 inputs. We give it the initial state, which we have just calculated from the pre-trained image model, and this summarizes the contents of the image. Then we give it a sequence of integer tokens, which have been converted using a tokenizer, so that the start marker becomes the integer 2, the word big becomes the integer 165, the word brown becomes the number 110, the word bear becomes 102, and so forth. So we give the decoder this entire sequence here, and then the last input is the same sequence, but shifted one time step. So the idea is that we want the decoder to learn that the start marker should map to the word big, and the word big should map to the word brown, and the word brown should map to the word bear, and so on, until we get down to the end marker, and then we're finished. And the way this works internally in TensorFlow is that TensorFlow first inputs the first integer to the embedding layer. The embedding layer then converts that integer into a vector with 128 floating point numbers, roughly between -1 and 1, because the neural network cannot work on integer numbers directly. Then we take that vector and input that to the first recurrent unit, and combined with the initial state, which was taken from the image model, it will then update the internal state of the recurrent unit, and it will output a vector. And what we show here in this diagram is that we have unrolled the processing through the time steps. So the arrow that you see here really means that the internal state is sent to the next time step. So when we get to this point here, we have the number 165. We will put that through the embedding layer and get some vector of 128 floating point numbers out. We will input that to the gated recurrent unit. Then we will take the updated internal state, we will process that, we will output a new vector and update the internal state again, and then we move to the next time step. And we continue this until we have processed the entire input sequence of integer tokens. What we get out of this is a sequence of vectors of 512 elements each. So that is output here and used as the input to the second recurrent layer. And then we do the same processing using these inputs, but we still use the same initial state taken from the image model over here that summarizes the contents of the image. And then we do the same and we get a sequence of vectors with 512 elements out, and we process that in the same way in the third recurrent layer. And then we get a sequence of vectors out again, but these have 512 elements, and we somehow need to transform that into an integer between 1 and 10,000 if we have a vocabulary of 10,000 words. So we do that using a dense or a fully connected layer, and then we continue doing that for each of the time steps until we have a sequence as output. When we are training this, it doesn't give us the correct output to begin with. At first, it just gives us random output, so we want to train it by giving it the correct sequence of integer tokens as the output, so that we compare the predicted output of the decoder with the true output that we wanted to produce. Then we backwards propagate the errors all the way through the recurrent units and also this dense layer here. But in this tutorial, we won't be updating the weights of this model over here. You can try that as an exercise and see if you can improve the results by doing that as well. And then we continue this process for millions of images until finally the decoder produces output texts that are close to what we want, so that it has learned to map from pixels over here to text over here. Now, when we are doing inference, we do this a little differently. Once again, we start by processing the image through the image model and we get the initial state out. But now we don't know what the text is, so we cannot input any words up here. What we can input is the start marker. So we use the integer token 2, which represents the start marker, and we input that along with the initial state that summarizes the image contents. And then we hopefully get the word big out. Then we can input the word big again up here and run that through the recurrent neural network again, and hopefully we will get the word brown out. Now, when you're running this on a GPU, for example, every time you want to run this through the recurrent neural network, you have to pack up the data and send it to the GPU, and then you get the result back. And there are different ways of doing that. We could only process one integer token at a time, but then we will have to also get the initial states of the recurrent units out, and then we will have to feed them back in for each iteration, for each token or each word we want to process. This makes the code a lot more complicated, and I'm not sure it's faster than what we are doing here because it's Python, so it's an interpreted language, and it has to transport data back and forth to the GPU and so forth. So the cleanest way of programming this is that we actually build this entire sequence of integer tokens and we send the entire sequence through the recurrent network in each iteration. So we do it for the start marker, and then we get the number 165 out, then we add that to the sequence, and then we input the same initial state and this sequence with two numbers now, and we process that whole sequence, but we only use the last number here, 110. Then we add that to the sequence, we process that entire sequence again with the initial state again, and we get this entire sequence out, but we only take the last number, and so forth. Again, this is very wasteful, but it's cleaner to program and it's better for a tutorial. If you're running something that needs to process thousands of images every minute, then you will program this more efficiently. Okay, so let's get to the implementation. And as usual, we have some imports. And I actually don't know why I say this every time, because of course we're gonna have imports. I think this is my start marker, so that now you know that the code is gonna start. So now you're ready for it. Okay, let's go on. So we have all of these Keras imports here, and then we have to load the dataset, and I will use the COCO dataset. And I have made a little Python module because I thought that the code in the COCO dataset was really bad. And you know how I feel about that, so I almost nearly hurled my PC into the ocean while I was yelling profanities. So anyway, I have made this module, and before you download the dataset, you can just change the data directory if you want. And you should note that this dataset is very large. The training data is 19 gigabytes, and the validation data is only about 800 megabytes. if you cannot download the whole training data, you can try and modify this code so it only downloads the validation data and then use that as the data set for training, but it's probably gonna overfit. You may still be able to learn how this works, even though the dataset is small. So you call this function and it downloads and it extracts the files if you don't have them already. And this dataset contains a lot of different data because you can do a lot of different things with this dataset. We only need file names for the images and we need the captions for the images. So I made this little function that retrieves that from the dataset. The training set contains almost 120,000 images. So we have this little helper function here, which can load and resize an image. And then we have a little helper function here, which can load an image from the training or the validation set, and then plot it and show all the captions. So we have an example of that here. And as you can see, it clearly shows a giraffe. And if you look closely, there's a second giraffe down here. And the images have at least 5 captions each. I think there were a few of them that had more. So we have one here, a giraffe eating food from the top of the tree. A giraffe mother with its baby in the forest, and I can almost guarantee you that it's a woman who wrote this. Okay, I'm not gonna go into a rant again this time, alright? But if you say what I just said, today people have become so sensitive that I might be called a sexist for this. But it's just a fact that women are far more interested in like interpersonal relationships, and you can't actually even see if this is a baby giraffe. It could just be further away so it looks smaller and it's behind a hill as well. But it's like family relationships, you know? When I think about distant family members, I have to go through my mind and sort of go through mathematical calculations to figure out exactly how I'm related with people. If you ask a woman, she knows instantly, oh, that's the relation. Oh, actually, I can tell a little funny joke, because about 7% of my audience is female. And I actually wish it was 100%. How great would that be? You know, all the guys, fuck off. Unsubscribe, get the fuck out of here. I only want women on this channel. Now, funny story. When I started at university as a computer science student many years ago, they had lumped together mathematics, computer science, and physics for many of the common classes. And in the first week, we had this introduction week where the older students would make a lot of jokes with us and things like that. So one of the jokes they made was that they said, you know what? There's only 2 girls out of 100 students on computer science. So this year we have decided that some of your classes in computer science will have to be in psychology instead, or something like that. Because there they had the inverse, where they mostly only had women. And they said this with a straight face. And I remember one of the women getting really pissed off. And she said, you know what? I studied computer science deliberately because I knew I wouldn't have any competition. I wanted to get some action as well. And it gets even funnier because a year or 2 later, she was running around school. I can't remember if she even had twins. But yeah, so she definitely got what she came for. Anyway, let's continue. So we load the pre-trained image model, VGG16, and using Keras, this is super easy. And this will also automatically download the model if you don't have it already. Now you can download it with all of the layers, including all the classification layers for the ImageNet dataset, and then it is more than 500 megabytes to download. Or you can remove all of the fully connected layers and then it is only 57 megabytes to download. Now, I will connect it with the last fully connected layer before the classifier. So we need to download the whole model, but I don't know because I haven't tried it. I'm running on solar power at the moment, so I'm limited in how much I can actually run this. But you can try and connect it to the last convolutional layer instead and it might work. It might actually even work better than what I have done here. And if you try that, then please write a comment under the video so the rest of us will know. So anyway, we can print a summary of the model here, all of the layers in the model. And the one that we will use as the transfer layer is this one here called FC2. And as you see here, it has the shape none and 4096, which means it outputs a batch of arbitrary size. And each of those is a vector with 4096 elements. So we get the transfer layer of the model out here. And then we build a new model in Keras, which takes the normal input for the image model. And then we take the output from this transfer layer instead. And then we can use this to run data through the pre-trained model and get the data out from the transfer layer. So we need to know the size of the images that we are inputting to the model, and we get that here. And we also need to know the size of the output, which we get here. Now, it takes a long time to process an image in the VGG16 model because it's so big, and we will have to process all the images in the training set multiple times because we have to train for 20 epochs. So 20 times we will go over the entire training set. And what we're gonna do is we're gonna make a cache file. So we process all the images in the pre-trained image model. We save the output, the transfer values, to this cache file so we can reload it very quickly. And here we have a little helper function for printing the progress of this because it takes quite a while. And here we have a helper function for doing this processing. And it just loads a batch of images, sends that batch through the VGG16 model, and then processes the next batch until we are done. This is a little wrapper function which saves the output to a cache file, and if that cache file exists when we call this function, then we load the transfer values from the cache file instead of processing it all again. And we have the same function just for the validation set instead. And running these functions take about 30 minutes on my GTX 1070 GPU. So now we have the tokenizer which converts text words into integer tokens, and you will have seen this in the last few tutorials on natural language processing and machine translation, but it's just slightly different here because all of the captions are stored in a list of lists, so we just have to process this with a nested for loop. And then, for example, for the first image in the training set, we have this list of captions here where we have added the start marker and the end marker to each of the texts, and you can see what they look like without those markers. However, the tokenizer from Keras needs a flat list of texts. Then we say that we only want to use the top 10,000 words in the dataset, and then we wrap the tokenizer class from Keras with a little extra functionality similar to what you saw in the last two tutorials. And then we can process the entire dataset of image captions so that this text down here, start marker, close-up of bins of food, blah, 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 becomes this sequence of integers here, and this text here becomes this sequence of integers here, and so forth. The problem we have now is that we have a dataset that consists of a NumPy array of transfer values that are output from the image model, and we have a list of lists with integers, so that for each image or each vector with transfer values, we have actually a list of sequences with integer tokens. Keras cannot directly work on this because for each of the images there's at least 5 captions, and we need to have one-to-one. So what we could do is we could throw away 4 of the captions for each image, but this is very valuable information and it has probably cost quite a bit of money to produce it. And it is most likely going to make our model better that we have 5 captions for each image rather than just 1. The other thing we could do is that we could replicate the transfer values for each of the images 5 times, 1 for each of the captions, so that we have NumPy arrays that match. These are bad solutions because either they throw away a lot of valuable data or they waste a lot of memory. A better solution is to create a custom data generator for Keras. So this is the function that will generate random batches of data during the training. First, we need a helper function that, given a list of indices for images, it will get a random caption and more specifically the sequence of integer tokens for that random caption. This function is then used down here, which is a Python generator function that has an infinite loop. I suppose the pronunciation is infinite. I don't know. But anyway, it repeats this for eternity so that it will just create random batches for as long as we want. So it starts by getting a list of random indices of images in the training set. Then it gets the transfer values for those random images. And then we use the helper function above that we just saw to get random captions or integer tokens for those captions for those images. Then we pad those sequences of integers with zeros, so they all have the same length as the longest sequence. Then we create the input and output data for the decoder by time shifting these sequences of integer tokens. Then we wrap all of this data in dictionaries where we name the data so we are sure that it is assigned correctly in our model. And then we return the data. So if we go back and look at the flowchart, what we have done now is that we have created a cache file with the transfer values down here, 4096 elements for all of the images in the training set. Then our generator function creates a random batch of data by taking some of these transfer values and the corresponding sequence of integer tokens, and then time shifting this sequence here so it becomes like this sequence down here. And it creates a whole batch of this data so that we can input that to the decoder model and train it. And let's go back down to the code. We will be using a batch size of 1024 elements because I want to keep my GPU fully loaded all the time. And we can then just test if the batch generator works. And we create a new batch like this. And these are the transfer values for the first image in the batch. And this is the sequence of integer tokens for that image. And it has just been time shifted one step down here. So now we can create the recurrent neural network, and we will use internal state sizes of 512 elements, and the embedding layer will output vectors with 128 elements. And we need to be able to input transfer values to our neural network, so we have that input layer here. And remember that the transfer values contain 4096 elements, but the internal state size for the recurrent units are only 512 elements. So we need this dense or fully connected layer to map those transfer values to only 512 elements. And I found that I needed this tanh function, otherwise it wouldn't work. So that the output of this layer are values between -1 and 1. Then we need an input layer for the sequences of integer tokens. And this none here means that the sequences can have arbitrary length. And here we create the embedding layer. And here we create the recurrent layers. And you will note that they all return sequences. Finally, we have a dense layer because the output of the last recurrent layer is a sequence of vectors with 512 elements each. And we want to convert each of those vectors with 512 elements into a vector with 10,000 elements so that we can take the argmax and get the integer token for the word out. Now, as in the previous tutorial, there is a bug in Keras, so we have to make a custom loss function, because normally you would have a softmax activation here, but because of our custom loss function, we only use a linear activation function here. We are using the functional API of Keras to build this, and this has actually not connected all of the layers in the neural network yet. So we have this helper function here that allows you to connect different inputs for the transfer values. And then it connects all of the layers in the neural network and returns the output of the final layer. So we use that helper function to create a model that we can train. As I described in more detail in the previous tutorial, there's a bug in Keras, so we cannot use the built-in loss function. And instead we have to make this custom loss function that uses this function from TensorFlow. I described this in much more detail in the previous tutorial, so I'm just gonna skip that here. Now we have to compile the model before we can actually train it. And I can't remember if I mentioned this in the previous tutorial, but in many of the tutorials I've used the ADAM optimizer. But I found in my experiments here, when I was trying to get all of this working, ADAM doesn't work very well for recurrent neural networks, apparently. It would train okay for a while, but then it would start to diverge and just completely break down. I just changed it with this optimizer here called RMS prop, and then it worked. And as I described in the previous tutorial also, because of this bug there is with the loss function in Keras, we need to make a separate placeholder variable for feeding the target data for the decoder. And then finally we can compile it so it's ready to train. Well, almost ready, because we want a few callback functions as well, so that we save a checkpoint during training after each epoch. And we also save a TensorBoard log. And if you either want to continue training because the computer broke down or whatever, you can reload the weights for the model here. Or if you don't want to train it at all and you just want to use a model that you trained a week ago to generate image captions for new images. And finally, we can train it. And each epoch took 7 minutes on my GTX 1070 GPU. And I ran 20 epochs, and you can try and run more and see if the model gets any better. If we had not used pre-computed transfer values from the image model, then each epoch would probably take 40 minutes to run instead of just 7. So we have saved a lot of time by doing it this way. So now that the model has been trained, we can use it to generate captions for images. And we have this helper function here. First, it loads and resizes an image. And because the image model is working on batches of images, so we just expand the dimensionality, and then we can input that to the image model. So we get the transfer values out. Remember, this is a vector with 4096 elements. Then we allocate the sequence of integer tokens that we will use to input to the decoder model. And then we use the integer token that represents the start marker, the 4 S's, so the decoder knows that now we are starting to generate a caption. And the caption is generated in this loop here. So as long as we haven't seen the end token and we haven't exceeded the max count of tokens that we want to produce, we wrap the data in a dictionary so that we assign the data to the correct inputs of the model. And then we run that through the model here and get the output. And once again, as I have explained before, we send the entire sequence of integer tokens into the decoder model on each iteration. And this is very wasteful, but the code would be a lot more complicated if we had to get the state of the recurrent units out when we call predict, and then in the next iteration we would have to feed those states back in. So because we already know what the model has output in the last few time steps, we are only interested in the last output. So what we get out here is an array with 10,000 elements because it's 1 hot encoded. Then we take the argmax, we get an integer, and then we use a tokenizer to map that back to a text word, and then we append that to the output text. And then we just repeat this loop. And when it's done, we plot the image and print the text that we have generated. So we can use an example here, and this is one of the images that I have used in previous tutorials, and it's an image of a parrot, and the predicted caption is a small bird perched on top of a tree branch. It's not 100% correct, but it's good enough. It shows that the concept probably works, and then you can experiment and see if you can make a much better model. It also depends on what the COCO dataset has. If the COCO dataset doesn't have any images of parrots, so let's try another image we have used in some of the previous tutorials. This is Elon Musk, and if you run this through the inception model back in tutorial 7, I think, something like that, the model got confused and said that this was either a sweatshirt or a cowboy boot, but our image captioning model actually gets it a lot better and says it's a man in a suit and a bow tie. The bow tie is incorrect. I can't see one unless it's very dark, but otherwise it's actually pretty good that it sees a man in a suit. So now let's try and use a model on images from the training or the validation set from the COCO dataset. So we just have a helper function here which can load an image from that dataset and run it through the image captioning model. So here we have the same picture that we showed above, and the predicted caption is a giraffe standing in a field next to trees. This is actually pretty good. And more importantly, it is not equal to any of the captions in the training set. That is pretty cool. So the image captioning model has learned to map the transfer values from the image model, which is a 4096 element vector, and that vector somehow encodes that there's a field and there's trees and a forest and there's a giraffe and maybe some other data, and then the recurrent decoder model has learned to map those features from the transfer layer into the correct words, and it has learned to string these words together in a grammatically correct sentence. That's pretty cool. So here's the key question. Is the image model a man or a woman? Now here's another example from the training set. So again, this is an image that the model has seen during training. So it has seen 5 correct captions for this. And what does the model produce? A bird is standing in the grass near trees. Now these captions in the dataset were produced with Amazon Mechanical Turk or something like that. So it's actually humans that have written them. And one of these is actually wrong. 2 zebras seem to be embracing in the wild. These are not zebras. These are giraffes. But anyway, it is easy to find examples in the training and validation set that the model can generate correct captions for, and it's easy to find examples that it cannot generate correct captions for. Maybe it just needs more training, but maybe you also have to improve the architecture. And a final example is this one. A brown bear is sitting in a grassy field. And here I experienced that, if you ran it for 1 epoch more or 1 epoch less, it would generate something quite differently. But something interesting here is that if you look at the human-generated captions, the word bear occurs in very different positions. And also none of the captions are identical to the one that we have predicted. I guess the closest one is this one, and especially this part here. But even so, our model has added the word is, and it doesn't use the word grassy area, it uses the words grassy field instead. So the data that we have given to train is actually quite varied sometimes. And even so, it still learns to extract meaning from the data. So the conclusion is that this actually works reasonably well and is quite impressive. But it's important to understand that this is not a human-like intelligence, alright? It's just a very clever and very advanced function approximator that takes image pixels and maps them to sequences of integers. It doesn't know what a giraffe is or what a bear is or anything like that. So as usual, you can download this tutorial by clicking on the link below the video.